Hey there, we're going to go ahead and get started on 4.2. So bear with me for just a sec. All right. 4.2 is here about nonlinear functions and equations, but now we're going to start talking about how to graph them and like different parts that are important and maybe even some application problems. So let's get to it. So graphing polynomial functions is the first section that we're going to cover. The graphs of polynomials are continuous and smooth curves that contains hills and valleys. We talked about that in 4.1. A turning point occurs when the graph changes from increasing to decreasing or decreasing to increasing. So increasing, increasing, decreasing. That's a turning point. Decreasing, 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 increasing. That's a turning point. So these are usually called vertices, hills, valleys, but now we're going to get curves. We're going to now give them a new name called turning points. Okay, a degree, the polynomial of degree n with n greater than or equal to 1 has at most n x-intercepts and at most n minus 1 turning points. And we talked about this briefly in 4.1, but we're going to get into detail about it and so you can see examples. A quadratic function has at most 2 x-intercepts. That's like it could cross the x-axis at most 2 times because the degree is 2. Turning points is going to have 1 turning point. There's going to be 1 vertex, okay? So it's 2 from the degree, which means that there's at most 2 x-intercepts. There doesn't have to be 2, but there could be 2, but not more than 2. And then at most, there's only 1 turning point. So that's 2 minus 1. A quartic function, which is degree 4, has at most 4 x-intercepts and 3 turning points. Doesn't have to have 3, but at most it will have 3. Okay. A constant polynomial function is where we just have a straight line. So that's where like there is no variable to be making curves and turning points. So that line is just going to be constant wherever that is. And it doesn't have a degree. The degree is 0. So these are just horizontal lines. No x-intercept, no turning points. So it says, give us a symbolic example of a constant polynomial function. Symbolic means like an equation. So yeah, anything that's equal to a number. So f of x equal 4, you could say f of x equal 15. F of x equal 5,000. It doesn't matter. If it's just a constant, then it's just a whole number. Actually, a number, it could be a decimal. Linear polynomial function. We know linear functions, they represent lines. There's no turning points in those either because the degree is 1. So we have x to the first power, or f of x equals x to the first power. So the degree is 1. That means at most it crosses the x-intercept at 1 time. And turning points, 1 minus 1, 0. So these are straight lines. It's not horizontal or vertical because those are constant polynomials. Linear polynomials have 1 x-intercept with no turning points, either positive or negative lines. Okay. Example 3 says, give a symbolic example of a linear polynomial that has the end behavior of negative infinity as x gets large. So we're looking for a negative polynomial. So I would say f of x equal negative 5x. They said negative 4x. That's fine. The slope just has to be negative. Why? Because it says f of x has to be going to negative infinity. as x gets large. So as x gets larger and larger and larger, this looks like it's going up. As x gets larger and larger and larger, the graph is going down towards negative infinity. So that is what we mean by a negative slope versus a positive slope. If you don't understand that, then pause that, rewind it, and watch it again, and let me know if you still have questions. A quadratic polynomial, we've seen these. The degree is 2, which means it has 1 turning point at most and 2 x-intercepts at most. Keep saying at most because it doesn't have to cross. You just have 1, or it could none. Remember? But at most it will have 2. There's no way it could have 3. So at most it'll have 2 x-intercepts, but it will only have 1 turning point because it's always the degree minus 1. If the a value is positive, then that graph smiles up like a cup. If it's negative, then it's down like a frown. Give a symbolic example of a quadratic polynomial that has the end behavior that tends to positive infinity on both sides of the graph. So we're looking for a positive graph. So any quadratic with a positive value, 4x squared, perfect. If we had negative 4x squared, then it would have been downward. So remember that a value, if it's positive, we're going to be up like a cup, tending to positive infinity. Okay. Cubic polynomial function, that means the degree is 3, which means at most there are 3 times it could cross the x-axis and 2 turning points. So you're going to have at most 2 turning points. These have opposite in behavior, just like an odd function. See, this is as x gets larger, the graph is going up. So this is a positive a value versus as x gets larger, this value starts going down. So this is a negative a value. This one is positive a value because of the positive infinity that it's headed to. This one's headed to positive infinity. This one is headed to negative infinity on the right-hand side. So when we get to our example, it says, if possible, sketch a graph of a polynomial that's odd. The degree 3 and has 0 x-intercepts. So would it ever not have any x-intercepts? No, it's not possible because it has to cross the x-axis at least once because of the end behavior. The end behavior is like one side's going down and one side's going up. So it has to cross this x-axis to make that happen at least one time. Okay, it could go like this. You know what I'm saying? But it's still got to cross at least once. It is impossible to draw with no x-intercepts because it's an odd function. Quartic, that's 4. 4th degree polynomial means it has at most 4 x-intercepts and 3 turning points. You can see that. The end behavior is the same. So positive, positive, negative, 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 negative. So this is going down towards negative infinity. These goes up towards positive infinity. And so that tells you what your a value is doing. If your a value is positive, you're in this situation. If the a value is negative, you're in one of these situations. Okay. If possible, give a symbolic example of a quartic polynomial that has 4 real zeros and the end behavior that tends to negative on both sides. So we're dealing with a negative a value and 4 zeros. And that's how you can write that negative a value. That's important because that's how you know if it's going to negative infinity. And then just pick 4 different values to multiply, and that would be your 4 x-intercepts. This means it crosses at -2. This means -1, +1, and +3. Those are factors. Quintic. fifth degree polynomial, that means it has 5 x-intercepts at the most, and that it has 4 turning points. So this is an example of that. 5 is odd, so that means the direction is going to be opposite, negative and positive, but the end behavior on the right-hand side tells us what type of graph this is. It ends up going up, so it's a positive graph. This one ends up going down, so it's a negative graph. This one ends up going up, so it's a positive graph. Remember, they don't have to cross at like all 5 times, but at most they could cross 5 times for a quintic. Okay, so this is an example. It only crosses once. But because of the end behavior, we know that it at least has to cross once. Because the only way you're going to have starting from the bottom and going to the top, or starting from the top and going to the bottom. That's the only way that can happen. So for our example, if possible, given a symbolic example of a quintic function that's odd and has a positive leading coefficient. So we can just choose a positive leading coefficient and just choose, the different values for this to be a quintic function. There we go. Just choose a quintic function, doesn't really matter. Remember, what odd means that only the exponents are odd. That's how you get an odd function. So you couldn't have x to the 5th power plus x to the 4th power. That's not an odd function. Okay. Odd symmetry is not the same thing as being an odd function. Okay. Use the graph of the polynomial function f to complete the following. Let a be the leading coefficient of the polynomial. So determine the number of turning points. I literally don't see any turning points. There are no turning points because this graph is always decreasing. There's no valleys. There's no hills. There's this weird slowdown, but it just continues to slow down. State whether a is negative or positive. So because this ends up going down, our a value has to be negative. So our a value is less than 0. That's it, because this graph ends up going down. And a is negative. Okay, so the same thing here. How many turning points do we have? I see 1, I see 2, I see 3. Estimate the x-intercepts. Those are these 2, 3. I see 3 of those as well. So I'm looking at -2, -1/2, and +1. -2, -1/2, and +1. Is my my a value positive or negative? My a value has to be positive because this is trending upwards. In the end, it all goes up. Okay, so a value is greater than 0. What is the minimum degree of f? Because there are 3 turning points, the degree in my mind is 4. And that says just that. Because there are 3 turning points, the degree is 4. So 3 plus 1 gives you the degree. If you have the degree, then you subtract 1 and be able to find how many turning points there are. Or at most, there could be. All right, example 10, same exact idea. Number of turning points. Number of turning points. I only see 1. Oh my God, every time I write off of that, it switches. I only see 1. Estimate the x-intercepts here and here. Okay, and so those are true estimations. -0.7 and 2.7. See, notice that we're writing those as coordinate points because they are coordinate points. Because this graph has the arrows down to -infinity, that means our a value had to be negative. So a is less than 0. The minimum degree, so there's 1 turning point. So 1 plus 1 is 2. This is a quadratic. Okay. It may not exactly be a quadratic, it could be a quartic function. But right now we don't know, so we just say at minimum it's a quadratic. At minimum it's a degree 2. Example 11, I see 1, 2, 3, 4 turning points. Woo. Which tells me that my minimum degree is a 5th degree polynomial, but we'll get to that. Estimate the x-intercepts. They are at here, 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 and here. Negative 2.8, negative 1.10, and 1.5. Again, on the test, I won't give it to you where it's weird. I will go over it and we'll make it make sense. And because my end behavior on the right-hand side is going to positive infinity, I know my A value has to be positive. So it's A is greater than 0. And because we had 4 turning points, 4 plus 1 is 5. The minimum degree is a 5th degree polynomial. All right, we're going to be adding in some of our concepts. We're going to be talking about turning points and local and absolute extrema. So let's pull it all together. Identify the turning points. Here's one here and here's one here. Remember, the local extrema happen at hills and valleys. So there's a valley here that looks like it's at -2. And there's a hill here that looks like on the Y value, it's at 4.5. So our turning points are going to be points, -1.8 and -2. And then we have 0.5 and 4.5. Now the local extrema are the Y values, -2 and 4.5. So local min is -2, local max is 4.5. So the difference between just identifying the hills and valleys is that when we list it as a turning point, we want to know the point, versus when we list it as an extrema, we just want to know the Y value, like the highest point or the lowest point. Any absolute extrema? The answer is no, because it goes forever down and forever up. So there are no absolute extrema. Evaluate f of x at the given values. So we're just looking and being able to read a graph. So when x is -3, 1, 2, 3, where is your Y value? It looks to be -4. When x is -1, I have 2 values, but one of them is a whole. So I'm going to go up here and define that as +1. And finally, when x is 2, it looks as though this is at -2. Boom. Is f of x continuous from -4 to positive infinity? I would say no, and the reason is because I have to pick up my pencil. So y'all see how concepts from last test are now coming into play? No, because there's a break in the graph. I'd have to pick up my pencil. Example 14, applying the following. Oh, we got piecewise function here. Complete the following rather. The function is x between -4 and -1. So from -4, you'd have -4. -3, you have -3, -2, you have -2, -1, you'd have 1. But it's not defined, so I'm gonna put an open circle. And there we have it. That is our first piece of this graph. The function is equal to -1 from here to 2. And then we already have the piece of the quadratic drawn from 2 to 3. So we are done. That's a piecewise function. There we have it. We just used each piece defined on the domain that they asked us. And that's it. Okay. Determine if it's continuous. I would say yes, it's continuous because I don't have to pick up my pencil to draw it. There are no holes. Last but not least, example 15. Oh, I'm sorry. I don't know if y'all got to see that. Yes, because there are not any breaks. In other words, you can sketch this graph without picking up your pencil. Okay. Number 15. When there are a small number of fishing boats in the large area of water, each boat tends to catch its limit each trip. So like if there aren't too many boats, then each boat can catch what it needs and then leave the water. But as the number of boats increase dramatically, then there becomes a point of diminishing return. Like it's too many boats out here. We're not all about to get the number of fish we can hold. So that's called diminishing return, where the yield for each boat begins to decrease, even though the number of fish caught by all the boats continue to increase. So we're catching more fish, but for me individually, I'm not catching as many as I could. You're not catching as many as you could because everyone is catching fish and there's just so many people out here catching fish. This can be modeled by this function where X is the number of fishing boats in hundreds and F of X is the number of fish in thousands of tons. Evaluate F of 4. So F of 4 is in between this first section. So F of 4 equals 4 because F of X equals X in that range. So what that means is if we have 4 fishing boats or 400 fishing boats, because it's fishing boats in hundreds, then we are catching 4,000 tons of fish. Yeah. 400 boats catch 4,000 tons of fish. Evaluate 6. 6 is in our next range. So we'd have to actually substitute 6 into that function. So we put 6 into this function. And we solve that. And we get 5.72 thousand. So 5,720. Tons of fish. The interpretation it says is if we have 600 boats that each boat is, that we're basically catching 5,720 tons. Finally, part C says solve. Oh, I thought we just did that. Oh, wait, that's not what it's asking us. See, in part B, it says put X as 6. So we wanted 600 boats. We're given 600 boats. This time we're given 6,000 tons of fish. And we're saying how many boats? Okay, so we're going to be solving backwards. So we just set this whole thing equal to 6, but the problem is 6 isn't valid because F of X equals X between 0 and 5, and 6 isn't in the domain for that part. So we can't use this first part. We'd have to use the second part. So we set it equal to 6 and we solve. Using the quadratic formula, because that's just a lot more difficult to actually try to solve a quadratic when you don't have that tool. You're going to move this 6 to the other side so that we set equal to 0, and then we can use the quadratic formula. Substituting those values in for A, B, and C, we find that X is equal to 6.5 or 13.5. So this basically tells us that there's either 650 boats in the water or 1,350 boats. And they're both valid because it's in between the range here of 5 to 15. So yeah, the interpretation for this is that when you have, if you want 6,000 tons of fish, either you're going to let 650 boats go out or 1,350 boats go out. But either way, you're still going to have that same number of fish being caught. I think this is the last one. May I just be making this up? Find the absolute maximum of the graph and interpret the results. So maximum is the maximum value. And so from the graph, I can see that it's at 7,000 tons of fish. But we could also solve for it using the vertex formula. So we use the vertex of this second set, negative b over 2a, x equals 10. So that means when 10 boats are in the water, or 1,000 boats rather, because 10 times 100, how many tons of fish are we catching? So you plug in 10 and you get 7. So 7,000 tons of fish are being caught, and that's the maximum number of fish we can catch when 1,000 boats are out at sea. Now that is all. Y'all have a great day, and we will talk about this soon.